All right, our final topic, number 11, is improper integrals. It's all about recognizing we have three situations we want to be on the lookout for. One is infinite bounds. Those are obvious. The second is if we have a bound that happens to fall at a infinite discontinuity. Those are at least we can plug in our two different bounds and see if it works. And then crossing. So we have an infinite discontinuity between the bounds of our integral or definite integral. These are all not that bad. I think D is not even that bad. But in general, let's just look. We can see already we have two problems where we can see some red flag bounds, right? Where they have bounds that are infinity. We need to rewrite these as limits so we can apply the fundamental theorem of calculus. Then the other two, B and C, we don't have those obvious problems, but we can look at the actual integrand, the function we were trying to integrate here, and we can see that both of them have a function in its denominator, and that function can equal 0. And if it equals 0, then we're at an infinite discontinuity because we're trying to divide by 0. So in this case, we know x cannot equal 0. That's going to be our problem child. That's where infinite discontinuity lies. And for this one, we could solve that out. We know that x cannot equal 5/3. That's where our vertical asymptote or infinite discontinuity lies for that problem. So we can already see all of our problem children, and now we can see in C that is one of the bounds. In B, 0 is not one of the bounds, but it is between those bounds of -1 and 1. So let's rewrite them. Okay, first one. This is fine. We need a limit. You can use any variable you want. Some folks are using t, that's lovely. Some folks are always using a or b, depending on whether it's the lower bound or upper bound. That's our problem. If you like that business, then we're doing a. All right, and we're going to go ahead and make sure we replace that negative infinity, our problem child, with that a. Leave everything else the same. And yes, if I were actually going to evaluate this improper integral, I would rewrite that as an x to the -1/2, but I am not, because that is not what the problem asked me to do. So I'm just going to leave it exactly as is, and the only thing I need to do is throw that problem child back in to my limit notation. So instead of saying we're taking this definite integral to someplace we can't at infinity, we are now taking it to some number and just nudging that number as close as we can towards that negative infinity. Okay, let's go ahead and jump to D, because D also has infinities. D has two problem children though, so as we discussed in class, we just need to split this integral into two separate ones. Any values we want. I like to go ahead, oops, I forgot to leave space for my limit. What was I doing? I'm going to start with the left because it just feels right to go left to right. You know, it's very like American of us in terms of like reading. So we will go ahead and say, let's have our a go to negative infinity. So I'm going to have an a. I'm going to rewrite everything. That would be a U sub problem if I had to solve it. Okay. And then I can choose any freaking number I want at all. Just as long as it's a green light, don't have any more problem children. I could look at this one. Technically, we have an x over e to the x squared. An exponential can never equal 0. So even though there is a denominator technically in this integrand, that denominator is not going to cause us any infinite discontinuities. She's lovely. So I can choose any number I want. 0 is the smartest number to choose, though just to prove a point, I've chosen weird-ass numbers in class. All right, now I'm going to add that. Oh, I almost forgot to leave space again. I didn't almost. I did. Leave space for my limit. We need to make sure that this also has a bound of 0, right? We're using that property of integrals that say that if I'm looking for an area under a curve and I go up to some value, and then I add that I can add those together and just be like, oh, this is the same thing, right? If I go from A to B, or if I use that C between, I'm not rewriting that property. We don't need to talk Calc 1. Bye. I don't know why I got excited. Anyways, so I need another limit. My other problem child was the positive infinity, so let's go ahead, replace that with a B. Let's do limit as B goes to. We know she's going to infinity, and we're just going to leave everything else the same. Cute. All right, so we know when we have the infinite discontinuities in our problem, we have to pay close attention because we can't just write the limit. Oh, let me do this one first. The limit as b goes to 5/3 from b to 0 of this nonsense. Because technically we haven't told the whole story. We actually do need to say what direction we're approaching that 5/3 from. So that 5/3, we started at 0 and we're heading towards it. We're coming from the left-hand side. That is crucial to have that direction on that. Okay, now the one where we have the infinite discontinuity in the middle, essentially what's happening is we have this graph. I'm going to assume square root means she's always positive. What? Oh, I got in trouble for this last year. Yes, I did. I got in trouble for this because technically it's not even defined after -0. See, just refound my error from last semester. I should really edit my tests instead of leaving them in my Google Drive unedited. So I think last year through an audible, I made that a cube root so that my drawing that I was about to draw was perfect. Okay, there we go. There we are. Fixed. Fixed. And so we're going from -1 to 1. So we set do the exact same work we did in D, not exact same, but very similar work to D. We need to split this into two separate integrals, one on each side of that infinite discontinuity. So we're going to have a limit. Let's go ahead and do -1 up to our discontinuity. We'll call that B. So we're going from 1 to B. We're doing this little portion right here, 1 to 0. And we're coming to 0 from the left-hand side. Cute? And we'll just go ahead. I'm going to rewrite this. And then we need to do the same thing. We need to add another. This time we're going to be starting at, I'll go ahead and do A. We're going to start at A. We're going to go up to 1. That's just terrible looking. I don't sometimes really question my choices. X to the -1/3 dx. And we do want to approach that 0. This time, the 0. Oh my God, this is weird because I don't want to sweep this way, but we have to get towards it from the right-hand side. The drawing is not nearly as glamorous as I want it to be. But yes, we can, if we think of it as going backwards, we start at 1 and we'll head towards that 0 from the right-hand side. So that is the way to split this up, where we are fixing all of our problem children. So 0 we are now avoiding, it's in the limit. So you can actually see all these things. Oh, they fall into our limit notation. And then the ones that were problems because they were infinity are also in our limit notation. So that is a skill in itself, just sort of rewriting this. Remember, I'm going to add a problem that I don't have in that spring exam this semester, where you have to actually do the whole evaluation of an improper integral and tell me whether it converges or diverges, because we have a full hour more than I had in class with my 151 in the spring.